Hello everyone, thank you for signing in and watching my live stream. I'm Mr. Matt and this is Dr. Tot. Would you like a cookie, Dr. Tot? And welcome to Algebra I. Today we're going to continue our conversation with absolute value functions, or about absolute value functions and their transformations. We're going to talk about evaluating absolute values, what an absolute value is, what the standard graph of the parent function of the absolute value is, or what it looks like, how to graph it, how to sketch it. That's y is equal to the absolute value of just x. Then we're going to talk about how to transform the absolute value function, how to shift the vertex around, pick the function up, place it at another point, then also scale it either by a stretch or a shrink factor, and also be able to interpret what a graph of an absolute value function equation will look like, or what the corresponding equation is to an absolute value function graph. Let me go ahead and share my screen with you. And just a reminder, these are live streams, so there's a little bit of a delay with the iPad, but I'll keep track of that. If you find these videos helpful, please like and subscribe to my channel. But otherwise, let's go ahead and get started by talking about what does the absolute value function represent, or what does an absolute value represent, and how is that function written or graphed. So the absolute value represents the distance from 0 a number is, or a value is, on the number line. So it's the distance from 0 on a number line. So the practical application is that it turns everything positive, and that's how most students remember it. And that's true. However, the reason why it turns everything positive is that -3 is the same distance from 0 as +3, for example. So if you look at a number line and you have 0 smack in the middle, -3 is the same distance as +3 on a number line. So this distance is the same as this distance. So that's why the absolute value of -3 is the same thing, as the absolute value of +3, which is 3. If you have any questions at any point, feel free to drop them into the live chat feed, or if you're watching this recording, you can post a comment below. Now, how is the absolute value function written or graphed? So the parent function, meaning the simplest version of the absolute value function, is y is equal to the absolute value of x, just x. And that looks like a v. And you can always recreate this function by taking a table. But in general, it's going to look like a v with a vertex at the origin 0, 0. So if we plot out some points here, and we're just doing a rough sketch, we're not doing anything fancy, and we take a table. So if we're evaluating y is equal to the absolute value of x, and we take a table, let's say, of -4, -2, 0, +2, and +4, when we substitute these values into the function y is equal to the absolute value of x, we're going to evaluate what the outputs are. Those are corresponding points on the function that we can plot and then connect together to sketch out an overview of the whole function. So when x is equal to -4, we'd have y is equal to the absolute value of -4. The absolute value of -4 is +4. So at x is equal to -4, y is equal to +4. If we were to evaluate what y is equal to when x is equal to -2, we would have y is equal to the absolute value of -2. The absolute value of -2 is +2, so at x is equal to -2, the function obtains a y value of +2. Similarly, if we input 0 for x, the absolute value of 0 is just 0. So at at x is equal to 0, y is equal to 0. Continuing on, we're just going to plug in the next 2 points. So the absolute value, y is equal to the absolute value of +2, which is just +2. And then y is equal to the absolute value of +4, which is also just +4. So now we have all of these coordinate points, well, 5 of these coordinate points, which is enough to sketch out a graph. So we already have our vertex at 0, 0. That's given. That's something that you can memorize about the parent function here. The parent function y is equal to the absolute value of x is always going to have a vertex at 0, 0, because if you input 0 for x, you get out 0. So 0, 0 is a point on this function. So if we plot out the other points, at -2, we're at +4. At -2, we're at +2, I'm sorry. And then at -4, we're at +4. At +2, we're at +2. At +4, we're at +4. So we're going to look something like this. My graph really isn't that exact. So these should be straight lines. And so the function y is equal to the absolute value of x looks like a V, like I've somewhat drawn it. I apologize, I'm not a great I'm not a great artist. But it does distinguish itself from the parabolas, the x-squared functions, because the x-squared functions are going to be U-shaped. They're going to have curves at the bottom, or it's going to have a curvature at the bottom. The absolute value function are 2 straight lines that meet at the origin in the parent function. So it has a V shape. If there's any questions, then please let me know. Now, we also learned last time of this transformational form that we're going to talk about in a little bit, but I just want to mention it now. So if we're trying to transform this function, we have y is equal to a times the absolute value of x minus h quantity plus k. And so this a value is your stretch or shrink value. We know that when a is equal to 1, there's no effect. If a is greater than 1, it's a shrink factor. If a is in between 0 and 1, then it's a stretch factor. And if a is less than 1, the above relationships still apply. But the whole function is flipped around the x-axis. This h value, that's your horizontal shift. Remember that your horizontal shift is opposite common sense. What do I mean by that? I mean that there is implicitly a negative sign attached to the h, or being applied to the h in the standard form of this transitional equation. that means that it's going to negate all values that are inputted that you would normally suspect to act in a certain way. So if we're talking about a horizontal shift, +2 would usually mean right 2. -3 would usually imply left 3 if we're talking about on the x-axis, because the negative numbers are to the left of 0, positive numbers are to the right of 0, so that's what common sense would imply. However, that negative sign is going to flip all of that around. So if it's -3, if your h value is -3, you normally think that's left 3, but it actually means right 3. If it says +1, that normally you would impute that that means right 1, but it's opposite common sense. That's actually going to be left 1. And then the k value, that does not have a negative sign attached to it. That's your vertical shift, and that goes with common sense. So if it's +1, that means up 1. If it's -3, that means down 3, so on and so forth. We'll have more work on this in just a little bit. First, remember that evaluating absolute values, the practical application is that it just turns everything positive. If it already is positive, then it remains positive. If it's negative, then it turns positive. So I'm going to give you 2 minutes. I'd like you to evaluate the following 4 absolute values. I'll keep track of the time in the upper right-hand corner and update it per minute. Okay, so the absolute value of -152 is positive 152 because -152 is 152 units away from 0 on a number line. The absolute value of -3 times 12. So you treat the absolute value bars just like parentheses. You need to do everything inside the parentheses first. -3 times 12 is going to be -36. The absolute value of -36 is positive 36. The absolute value of positive 85 is just 85. It remains positive. And the last one, the absolute value of -2 times 14. Again, we have to do -2 times 14 is -28. The absolute value of -28 is positive 28. If you have any questions, then please let me know. Otherwise, I'd like to work a little bit with graphing functions based on that transformational formula that I explained briefly above. And actually, let me go and grab that and plug it back down here so you have it. And just make sure that my camera's not in the way there. So remember that the translational form of how we can picture these things, just like when we think about a standard straight line, when we think about a straight line, we have two different forms of the equation of a straight line. We have the standard form, that's ax plus bx is equal to c. Ax plus by is equal to c. And the standard form really doesn't tell us very much. We can't look at the standard form and visualize what the line looks like, or at least most people can't. And that's why we organize the information in terms of the slope-intercept form. The slope-intercept form allows us to visualize the line a little bit more easily. And so that's why it's useful. This translational form does the same thing. If we're looking at the standard form of an absolute value function with it all mixed up, it doesn't really make much sense, or we can't really picture it as easily. But if we have it written in this a times the absolute value of the quantity x minus h quantity plus k version, that allows us to very easily visualize where we're putting the vertex, so where we're picking it up and dropping it off, and then also to look at the scalar application, that a value, look at the stretch or the shrink value, or whether it's negative and flipped around the x-axis. So it allows us to start to picture in our minds what this function looks like. So I'm going to give you 3 minutes. I'd like you to look at 1 and 2. After the 3 minutes, I'm going to solve 1 and then give you a little bit of extra time to look at 2 again. Okay, so if we look at number 1, g of x is equal to x, the absolute value of x plus 3, quantity plus 2. So let me just get this stuff down here. Oh no. I want all of this. Save that for later. So if we plot this out, actually let me do this. This would be easier. Okay, so if we plot this guy out, so the absolute value, the parent function, would look like this. It has a slope of positive 1 when it's greater than 0, and it has a slope of negative 1, when it's less than 0. Okay, so this is f of x is equal to the absolute value of x. That's the parent function. If we're going to plot now g of x, the h value is positive 3. Remember, the h value is opposite common sense. So if the h value is positive 3, normally we would think right 3, but it's opposite common sense, so this is actually left 3. The k value is positive 2. That goes with common sense, so that's going to be a translation up 2. So we're going to take this vertex, and we're going to go left 3, and we're going to go up 2. And so our new vertex is going to be right here. And we didn't do anything with a scalar. We didn't stretch or shrink it, so it's going to have the same increase of 1. Notice that these grid lines really help when I'm plotting this, because a slope of 1 just means that it's going through the diagonals of each of these little squares. So this guy right here would be g of x is equal to the absolute value of x plus 3, quantity plus 2. All right, so I did that guy in blue. I'll do this guy in orange. So the h value is negative 4. Remember, the h value is opposite common sense, so negative 4 on the x would usually mean left 4. Opposite common sense meaning this is going to be right 4. So this is a shift right 4. And then the k value is negative 1, so that goes with common sense. That's down 1. So we're going to go right 4, down 1. So that's our new vertex. And then we just draw in, we didn't do anything with the scalar here either. So we're just going to draw in the plot, assuming the slope of 1, these two sides of the absolute value function. So this guy is h of x is equal to the absolute value of x minus 4. Excuse me, the absolute value of x minus 4, quantity minus 1. If you have any questions, then please let me know. Otherwise, let's look at number 3 and 4, numbers 3 and 4. 3 asks you to plot j of x is equal to 3 times the quantity of the absolute value x plus 1, quantity plus 2. 4 is k of x is equal to 1/2 times the absolute value of x minus 2, quantity plus 3. Oops, I'm sorry, my iPad disconnected there. Let me reconnect. My bad. Sorry about that. So number 4, k of x is equal to 1/2 times the absolute value of x minus 2, quantity plus 3. So first start with the parent function, y is equal to the absolute value of x, and then go from there to think about where is the new vertex. And then you might want to plot out, once you have the vertex, pick 2 points on either side of the vertex to test in the actual equation, and you find what the output is at that specific input, and that will allow you to connect the two lines together to create the actual sketch of the graph. The reason you have to do that here is now we have these scalars. We have these a values of 3 and 1/2. So the slopes of the two sides of your v are not going to be 1. It's not going to be as easy as connecting the little diagonals of the square that I did before, or my grid paper. Here, it's actually going to be a different slope. So you have to find 2 points, and plot the lines out. So I'll give you 3 minutes, and then I'll give you the solution. And I'll keep track of, well, let me back these out, and I'll keep track of the time down here. Okay, so if we start with just a plot. Sorry, I can do better than that. And we're going to just draw in the absolute value of x. That's just y is equal to the absolute value of x, meaning a standard y is equal to x and y is equal to negative x when x is less than 0. So this is f of x is equal to the absolute value of x. Now let me do number 3 in orange. So first I'm going to start with the vertex. The vertex, I have a h value of positive 1. That's opposite common sense, so that's going to be left 1. Oops. I have a k value of positive 2. That goes with common sense, so that means left 1, up 2. So I'm going to go left 1, up 2. And so this is my new vertex. And now I have an a value of 3. So what I can do is write out a little table. I know that negative 2, that my vertex, negative 1. My vertex occurs at x is equal to negative 1. So I'm just going to pick 2 points to the left and the right of negative 1 in order to test where this function actually lies, so then I can connect the dots and draw a sketch out. So let me actually get some space here. Let me take this. So if I draw out a table, and I need to go on opposite sides of negative 1. So I'm going to maybe test negative 3 and positive 1, because those are both 2 units away from negative 1. Substituting negative 3 into the function, 3 times the absolute value of x plus 1 quantity plus 2. So in other words, j of 3 is equal to 3 times the absolute value, j of negative 3, not positive 3. J of negative 3 would be 3 times the absolute value of negative 3 plus 1, quantity plus 2. So we're going to have 3 times the absolute value of negative 2 plus 1. The absolute value of negative 2 is 2, so we're going to get 3 times 2, quantity plus 1. And I apologize, my iPad keeps on disconnecting. So we get 3 times 2 plus 1. That should connect there in a second, I'm sorry. 3 times 2 is 6. 6 plus 1 is 7. So when x is equal to negative 3, y is equal to positive 7. Then we can do the same thing for j of positive 1. We're going to have 3 times the absolute value of 1 plus 1, quantity plus 2. You're going to notice that this is going to have the same result because remember the absolute value function is symmetrical around its axis of symmetry, which is the line where the vertex is occurring, the vertical line where the vertex occurs. 1 plus 1 is 2, so we get 3 times the absolute value of 2 plus 2. Excuse me, not plus 2. I'm sorry. I don't know where I carried this 1 from before. So this should all be 8 in the first calculation. I'm sorry, I had a 1 there. These should be 2. Let me highlight what I just corrected. So I erroneously put 1 there, as I have right there. That needs to be a 2, and I apologize. I don't know why I put 1. So this should be 8. So in our second calculation, the absolute value of positive 2 is just 2. So again, we get 3 times 2 plus 2. 3 times 2 is 6. 6 plus 2 is 8. So at negative 3, we're going to be at positive 8. That's right here. At positive 1, we're going to be at positive 8. And so now I can connect these two dots together to get this side of the function. I can connect these 2 dots together to get that side of the function. And that is the sketch of j of x is equal to 3 times the absolute value of x plus 1, quantity plus 2. I'm going to sketch k of x in blue. So I have an h value of -2 and a k value of +3. The h value of -2, normally that would mean left 2, but it's opposite common sense. So this is a shift right 2, up 3. So from the origin, 0, 0, I'm going to go right 2, up 3. So this is my new vertex. And now I need to test 2 points on opposite sides of x is equal to 2. So I'm going to, again, draw a table here. And I'm going to test x is equal to 0 and x is equal to +4, because those are both 2 units away from x is equal to 2. And so plugging 0 in, I'm going to get, let me do that right here. So k of 0 is going to be 1/2 times the absolute value of 0 minus 2 quantity plus 3. 0 minus 2 is -2, so this is going to be 1/2 times the absolute value of -2 quantity plus 3. The absolute value of -2 is +2, so this is going to be 1/2 times +2 quantity plus 3. 1/2 times 2 is 1. 1 plus 3 is 4. So at x is equal to 0, y is equal to 4. If I were to solve for the value of k of 4, I'm going to get 1/2 times the absolute value of 4 minus 2 quantity plus 3. Four minus 2 is 2. So this is going to be 1/2 times the absolute value of 2 plus 3. The absolute value of 2 is just 2, so this is going to be 1/2 times 2 plus 3. 1/2 times 2 is 1. 1 plus 3, again, it's the same value because the absolute value function is symmetric. So at 0, we're going to be at 4. So we have 0, 4, and 4, 4. So this function is going to look like this. So this guy is k of x is equal to 1/2 times the absolute value of x minus 2 quantity plus 3. If you have any questions, then please let me know. Now, in our last few minutes together today, I'm just going to touch on the process of solving an equation that contains an absolute value function. So notice that the absolute value of some number, let's call it a, is actually equal, the absolute value of the negative form of some numbers, so the absolute value of -a, is equal to the absolute value of +a, because that just is both of those are just equal to a. Just as, notice, a squared, a quantity squared is the same exact thing as -a quantity squared, right? Because the negativity cancels out when you raise anything to an even power. So when you have -2 squared, for example, that's -2 times -2. The negativity cancels out. So we know that when we do the opposite operation of rooting both sides in order to get rid of an exponent, in order to get rid of a squared exponent, we take the square root. But when we do that to both sides of an equation, we have to consider the negative and the positive result to account for this phenomena that occurs when squaring to an even exponent. The same phenomena occurs when we take the absolute value, because the absolute value of a negative number is equal to the absolute value of its positive counterpart. And so when we do the opposite operation of removing the absolute value bars from an equation, we have to consider both the positive and the negative result. Meaning that when you're solving equations that have an absolute value, that have a set of absolute value bars in them, you're going to obtain two answers. One from the positive result and the other from the negative result. Just as in a squared function, when you have a variable squared and you have to take the square root of both sides in order to solve and isolate for that variable, you're going to end up with two answers, a plus and a negative. Now, it matters how complex the equation is as to whether those are exactly the same values and just one is negative and the other is positive. It's usually not that way. They usually are distinct values from each other unless for some reason the graph is exactly symmetric around the y-axis or a few other conditions as well. But you can't just assume that it's just the positive negative. You have to actually go through the algebra. So for example, if we were to solve this guy, we have 3 times the absolute value of x plus 5 is equal to 21. So I'm just going to start. My objective is to get the absolute value stuff by itself. So everything that's on the outside of the absolute value bars, I need to cancel out preeminently. I need to go at it proactively or before I even start to deal with anything with the absolute value bars. So I'm going to look at that 3, which is preventing the absolute value quantity from being by itself. The 3 is doing what to the absolute value quantity? It's multiplying into the quantity. So I'm going to do the opposite operation of dividing. So if I divide by 3 on both sides, remember in math you can do anything you want as long as you do the same thing to both sides. Same thing to the left as you do to the right. Same thing to the numerator as you do to the denominator. Other than that, you can practically almost do anything you want. There's a few exceptions, but practically. Notice on the left-hand side, the 3's will cancel out, and so we get the absolute value of x plus 5 is equal to 21 divided by 3. 21 divided by 3 is 7. So we get the absolute value of x plus 5 is equal to 7. Now, in order to remove these absolute value bars, I need to split this equation into 2 different versions. One is going to be considering the positive result. The other is going to be considering the negative result, because we have to account for that phenomena that the absolute value bars will remove negativity. So really we have 2 options, because negative 3 and positive 3 are both 3 units from 0. So as inputs they would both work. So when we're doing the opposite operation of removing the absolute value bars, just like division is the opposite of multiplication or subtraction is the opposite of addition, when we remove the absolute value bars, we have to account for that phenomena. So the positive version on the left is just the equation written without the absolute value bars. That's just going to be x plus 5 is equal to 7. On the right-hand side, when we consider the negative, you remove the absolute value bars, so nothing changes about the left-hand side, but you negate the output. So negate the 7 and turn it into a negative 7. So solving here, we're going to have x is equal to 7 minus 5. So x is going to be equal to positive 2. And x is going to be equal to negative 7 minus 5. So x is also equal to negative 12. So that's just a little introduction into solving equations with an absolute value bar, with absolute value bars. We're going to get more into this, and I'll focus heavily on Friday on solving these types of problems. If you have any questions at all, please drop a comment below. If you find my videos helpful, then please like and subscribe to my channel. Otherwise, I hope you all have a wonderful night. Tomorrow's a writing day, so you feel free to join me for that. If not, we'll continue in our discussion about absolute value functions on Friday. And Dr. Tot, do you want to say goodbye to everybody? You want for a cookie? Come on. You got to say goodbye. Come on. You say goodbye? Can you say bye? Can you say bye? Come on, it's more. Okay, that's good. Thank you guys very much for watching. I hope you have a wonderful night. I'll talk to you on Friday.